Hello everyone, and welcome to our video set about Shor's algorithm. This algorithm is one of the most important components of QKD, therefore it's important for us to have a good grasp of it as we continue in our trek through quantum cryptography and communication. First, let's start by explaining why this algorithm is so important. Currently, computers rely on RSA encryption in order to keep our information safe. In broad strokes, this encryption technique makes use of the fact that prime numbers are very, very difficult to find. RSA encryption jumbles information using a large number n made of a product of two large prime numbers. In order to decrypt the data, we need to know these two numbers. Finding larger and larger prime numbers is thus very, very interesting from a cryptography point of view. In fact, you could make quite a bit of money by finding them because they're so difficult to find using our classical computers. We basically need to go through trial and error and hope we stumble upon one. In this video, we will show you how the nature of quantum computer is such that finding these prime numbers is a little bit easier. This video set will be divided in two parts. First, we will explain the mathematics of Shor's algorithm with nothing quantum just yet. In the second video, we will tell you why quantum computers can perform this algorithm so quickly and successfully. So, let's start with the first part, the basic fundamental mathematics of Shor's algorithm, which has nothing fundamentally quantum about it. To factor a number n, Shor's algorithm starts with some random guess g. The key aspect of this algorithm is that it transforms this guess g into a much better guess that does in fact share a factor with n. So, how exactly can we do this? We begin with our number n, which we need to factor in order to decrypt the message. We realize that we don't actually need to find a pure factor of n. Thanks to Euclid's algorithm, we only need to find a number that shares some factors with n. But we'll get into that later. Let's take a random guess g, which is just a whole number smaller than n. For big numbers, making a correct guess is pretty unlikely, which is where this algorithm comes in. Thus, we want to improve our random guess g, and to do so we use the following trick. For any pair of whole numbers that don't share a factor, if we multiply one of them by itself enough times, eventually we will get some whole number multiple of the other number, plus 1. G to the p equals mn plus 1. For example, 7 and 15. While 7 squared isn't one more than a multiple of 15, and neither is 7 cubed, 7 to the 4th is. This works for any whole arbitrary numbers, as we will see coming up. Now, we can rewrite the equation in the following way. G to the p over 2 plus 1 times g to the p over 2 minus 1 equals m times n. By rewriting it in this way, we've done something quite remarkable. We changed our equation such that we have an expression in which a large number is made up of a product of two numbers. In other words, we have something times something is equal to a multiple of n, which is exactly what we're trying to find, factors of n. Here is where Euclid's algorithm is useful. Maybe our guesses are not direct factors of n, but share factors with n. Let's illustrate this with a quick example. Say the number we're trying to find is n equals 15, whose factors are 3 and 5. We start by guessing g equals 7, and we try to find values of p until we get to p equals 4. Now we have 7 to the 4 over 2 plus 1 equals 50, which equals to 2 times 5 times 5. 7 to the 4 over 2 minus 1 equals 48, which equals to 2 times 2 times 2 times 2 times 3. So we can see that these two numbers are not directly 15, but they share factors of 15. Finally, 7 to the 4 over 2 plus 1 times 7 to the 4 over 2 minus 1 equals to 2 to the 5 times 5 times 15. Now, this is all fine and good, but there are some caveats we have to mention. Firstly, if the guess is a multiple of n, and therefore the other guess is a factor of m, neither would be of use to us. We failed at our mission of finding a good prime number. Secondly, if the power p is an odd number, p over 2 will not be a whole number, and thus we'll get an irrational number which cannot be a factor. Therefore, that's not a possibility either. Armed with these two caveats, we can proceed. If we look back at the equation from the beginning, g to the p is equal to m times n plus 1. We see that in order to turn our initial random guess into a good guess, we need to know how many times to multiply our guess by itself until we get a multiple of n plus 1. In other words, we're trying to find p. Unfortunately, for a normal computer, this is a trial and error process that could take forever. This, however, is where quantum computing comes in. In the next video, we will explore what makes this algorithm quantum and how we can finally obtain prime numbers quickly and somewhat easily.